All right, welcome to this explainer. Today, we are embarking on a really wild mathematical journey. We're going to connect the absolute purest number theory directly to the literal fabric of spacetime. Seriously, if you've ever wondered how abstract algebra could possibly dictate the shape of the cosmos, or even the rules of quantum mechanics, you are in exactly the right place. We're going to translate the rigid boundaries of the Adelic Langlands Program into actual physical reality. Here's a quick roadmap for our deep dive today. We'll start by tackling the non-commutative problem, then unlock the math with the Satake isomorphism. After that, we'll look at Rankin-Selberg field convolution, map that onto emergent spacetime curvature, and finally wrap up with the universe as a quantum error-correcting code. Okay, part 1. The non-commutative problem, or as I kind of like to call it, the absolute chaos of phase dispersions. We really have to start with a fundamental question. Think about this for a second. How do you actually measure a volume that is constantly fluctuating? In classical physics, properties are commutative. They play nice. But in quantum mechanics and advanced operator theory, the order of operations totally changes the result. And that creates immense mathematical friction when we try to pin down absolute boundaries. When you have matrices, let's call them A and B, and they just don't commute, their non-abelian phase interactions create these incredibly irregular varieties. Notice the determinant of their combination, represented as A plus U, B, U star. It just fluctuates wildly as the unitary group varies. These irregular, nonlinear geometries completely escape classical complex optimization techniques. You literally cannot track the individual unitary orbits effectively using standard real or complex numbers. It's a mess. So how do we bypass this chaos? Well, we decompose the global determinant over the Adel ring. We split it right into two halves. First, you've got the infinity component, which represents our continuous, warpable, real, and complex numbers. Then you multiply that by the discrete non-Archimedean components, basically the product of all the p-adic prime number-based traces. This equation literally splits that chaotic phase information into manageable, discrete channels. Which brings us perfectly to section 2, the Satake isomorphism. This is the mathematical key we need. Now, check out the core mechanism happening in the denominator here. The local Hecke operator trace takes those wild, unpredictable fluctuations and, almost like magic, transforms them into a perfectly smooth polynomial function of prime numbers. By mapping local determinants to the characteristic polynomials of Satake parameters inside the Langlands dual group, we translate totally erratic matrix geometry into an exact L function, L sub p of s pi. Prime numbers essentially become an arithmetic vice, clamping down on the phase variance. And this bound identity brilliantly illustrates how that clamp actually works. Look at the right side of the inequality. When we evaluate this strictly at the 4D physical mass scale, where s equals 1, the absolute maximum limit of our chaotic determinant is perfectly capped by the regularized Riemann zeta function. The primes form an inescapable ceiling for physical reality. There's just no way around it. Just to ensure we're all completely following the math, let's lock in this crucial definition, the global unramified automorphic partition function. Sounds heavy, right? But just think of it as the absolute limit of computational bandwidth for the entire universe. The total informational budget across all number fields has to balance. That means quantum field interactions can never, ever exceed this fixed arithmetic threshold. Grounding all this pure math back into physical reality, those discrete p-adic traces act exactly like a digital filter. Through a continuous real number window, we get this illusion of indeterminacy, tumbling chaotic volumes. But the p-adic error correction applies a massive mathematical compression. It snaps the chaotic fluid volume back onto a rigid baseline, stabilizing the quantum vacuum into a perfect, absolute holographic framework. All right, let's jump to section 3, Rankin-Selberg field convolution. This is where things get really interesting because we're going to start mixing quantum fields. When these fields actually interact, the cross-channel information exchange is computed by this exact degree n squared polynomial. We take operator A with its Satake parameters alpha and operator B with its parameters beta. Their cross-entropy is calculated by tensor producting them together, basically calculating every single cross-channel eigenvalue combination. Next, we literally unfold this global function using an Eisenstein series, mathematically integrating right across those non-commutative matrix sheets. Think of the Grothendieck-Riemann-Roch push-forward as this sort of cosmic dimensional compactor. It takes massive, high-dimensional arithmetic data and forces it straight down onto our observable four-dimensional spacetime. It acts as an absolute energy clamping mechanism.
So here's the huge takeaway. The cross-entropy of two competing quantum fields is strictly regulated by the primes, which squeeze their volume limits. Look closely at the explicit arithmetic squeezing equation there. When two fields intersect, like, say, merging black hole horizons, they can not just bounce against each other with arbitrary phase mismatch. The prime numbers literally squeeze the fields together, permanently preventing the generation of unbounded, infinite energy states in the vacuum.
Moving on to Section 4, Emergent Spacetime Curvature. We are finally translating this hardcore math into cosmology. So what happens when that determinal bound is fully saturated? Well, the non-abelian phase transitions overflow, and that forces a conformal warping of the continuous macroscopic metric tensor. Look at the conformal potential equation omega x. It is driven precisely by the logarithmic derivative of our saturated Rankine-Selberg convolution. The internal arithmetic stress is mapped directly onto the spacetime metric, generating actual physical curvature. This saturation point basically acts as physical mass density. See the formula for the arithmetic stress factor, K sub A of n? It computes the exact coupling constant locked to the prime conductors. Plug that directly into the 4D Ricci curvature tensor R mu nu, and the result is just stunning. What we conventionally call gravity is simply the universe absorbing extra non-commutative phase that the local primes couldn't handle. Which leads us to this massive realization. Gravitational curvature is the physical expression of a saturated information-theoretic bound. Really think about that for a second. What we experience as solid matter is simply regions of maximally compressed, unramified arithmetic data. Gravity isn't just some arbitrary pulling force. It is the absolute necessary geometric distortion required to maintain the structural stability and unitary closure of a massive algebraic network. Literally, it stops spacetime from tearing itself apart. And that brings us to our final stop, Section 5, Quantum Error Correcting Code, viewing the universe itself as a computer. By partitioning the dual matrix sheets, the eigenvalue intersections transform into a vast array of physical qubits, and they are protected by a stabilizer group of Hecke operators. The logical code space is exactly the invariant vacuum state under the action of these prime number-based stabilizers on the Brouhat-Titz tree. The mathematical properties of the Adelic Langlands Program perfectly mimic the architecture of a fault-tolerant quantum computer. And check this out, that Satake determinantal polynomial we unpacked earlier. When you evaluate it at the mass scale, it actually functions as a massively parallel entangling logic gate. Because the eigenvalues are so rigidly locked to a semi-simple diagonal matrix, this unitary operator acts exactly like a fault-tolerant circuit. It measures and processes the system without leaking any phase information to the environment. Let's quickly walk through the procedural math of how this cosmic code actually detects a non-commutative perturbation and uses global symmetry to correct it. Step 1. A local phase error introduces ramification at a specific prime. Step 2. The system detects this as a non-zero error syndrome. Step 3. It forces a global geometrical adjustment. And finally, Step 4. The metric relaxes and the error is wiped out. See, the global L function physically damps down that phase slip, forcing the local conductor exponent right back to zero. Step by step, the continuous Archimedean sector, which is our observable space, instantly adjusts its local metrics to absorb the anomaly. The error is cleanly corrected, and the quantum lattice relaxes right back into its protected, unramified baseline. I want to leave you with one final kind of mind-bending thought. If the very hardware of our cosmos is an active error-correcting code, what other absolute laws of physics are merely arithmetic waiting to be decoded? The smoothness of our reality isn't some random accident. It is the direct result of infinite code distance being actively suppressed by prime number topologies. Think about that next time you look up at the stars. Thanks so much for joining me on this mathematical journey through the Adelic Langlands framework.